ಮತ್ತವರಿಗೆ
ಯಾರಿಗೆ ರಾಯೇಶ್ವರ ಹುನಗುಂದ್ ಇದು ಗೂಗಲ್ ಮೀಟ್ನಾಗ ರಾಯೇಶ್ವರ ಹುನಗುಂದ್ ಅಂತ ಬರ್ತಾ ನೀನ್ ಇದನ್ನ ಇಮೇಲ್ ಐಡಿ ಚೇಂಜ್ ಮಾಡಿ ನಂದಲ್ಲ ಅದು ಬರುತ್ತೆ
ನಿಂದ ಕಟ್ಟಿನ ಅದನ್ನ ಒಮ್ಮೆ ಹುನಗುಂದ ರಾಜೇಶ್ವರಿ ಅಂತ ಐತಿ ಇದೇನಿದ್ ಬರ್ತ ನೋಡಿದ್ರೆ
ಇಲ್ಲ
ಇಲ್ಲ ಬದಿಲ್ಲ ನೋಡು.
Yes, sir.
ಫೋಟೋ ತೋರ್ಸಕತ್ತೈತಿ ಅದು ಫೋಟೋ ತೋರ್ಸ್ಬರ್ತಲ್ಲಿ
Okay, sir. I have given two links. One is YouTube and another one is Google Meet. So in the Google Meet, there is a limitation of 99 members. So if you are not able to join in the Google Meet, please do join in YouTube. So 1 minute. So today we shall hello. Those who are in YouTube also, they can view it and they can hear my voice. So those who could not get into the Google Meet, they can join with YouTube. So I have provided the same link in yeah. So all of you mute yourself so that there will not be any disturbance in the class. So you have all of you are familiar with Fourier series, right? So today I'll be starting with Fourier transforms. And before that, in your BSc classes, you have studied Fourier series. So can anybody who are in Google Meet, can you just tell me what can you do with Fourier series, or what do you do with Fourier series? Yeah. So by the way, let me introduce myself. So I am Dr. Sankarshan BM. I am working in National Institute of Engineering, Mysuru, as an assistant professor in Department of Physics. I completed my PhD in University of Mysore in 2018 and in radiation physics, and my topic was on Compton scattering. So today, next 5 classes, I'll be engaging the mathematical methods of physics. So in this, we have got 4 blocks. So the first one is the linear vector space and Fourier transform. In today's class, we shall start with Fourier transforms, and in the next class, we shall go for linear dependence and independence of vectors, and also the matrix representation. And then in the next coming classes, I will be dealing with tensors, and then differential equations and integral equations, and special functions. So because we have to finish it within 5 to 6 classes, I'll be rushing through the things and I will be pointing out the main topics and main things that you have to observe. So here, if possible, keep a sheet of paper and pen along with you so that along with me you can solve some of the problems. So even though we display the problems, unless and until you see how to solve it, you'll not be able to actually get into it. So therefore, it's always better to uh, keep a pen and paper along with you whenever you come for a mathematical class, right? So for a physicist, math is a language for the physics people. So whatever you want to express, you would be expressing in terms of mathematics. So it is called queen of physics, mathematics. So you have to understand how to deal with mathematical principles, and also you should know how to solve certain things. So that is why there is a paper in the first semester itself for solving the mathematical problems. So here, whenever we see this Fourier integral, before we see actually what's the Fourier integral, you should know the Fourier series. I'm talking certain things, right? The waves that you observe, if you do, analyze the voice that is coming out. The moment I say voice, there is a wave which would be coming out, right? Let me say, so say for example, whatever I speak, if I say it will be something like this. I don't know exactly how to solve this mathematically, right? So let's leave this sort of a complicated wave. If I just take a wave, a square wave or a step wave, it is not so easy to solve this. So whenever we take such a kind of wave, we want it to be expressed in terms of sine and cosine. We know how to solve even the integration, differentiation, and all those things in sine and cosine waves. So therefore, what you did in the Fourier series is actually dividing this or resolving a wave, a given wave, into sine and cosine form. So rather than taking a complex form like the speech or the words that we speak, because we would be producing waves of which has got a combination of so many waves of different frequencies and different amplitudes, we can just consider a wave, a simple wave like this. Now let me say, if I plot x in the x-axis, and if I say this is f of x, so rather, if I take this x and if I consider f of x in the y-axis, now if I define a step function, that means to say it would be having a value equal to certain, say f of x is equal to 1. If I consider this as, say, minus a and this as plus a, or for simplicity, let me take this as point A and point B. So here, if I want to define this function, I would be defining this function as f of x is equal to 0 if x is less than a, and 1 if x lies between a and b, and 0 if x is greater than b. So that means to say that here a function exists only between a and b. So whatever the terms that we take, if we take from minus infinity to plus infinity, we would be solving using Fourier. We had solved using Fourier series. So the moment you solve this sort of function using Fourier series, then the actual function that you will be getting would be a sum of so many waves, which you can represent it by sine and cosines. So the moment you express that, if you want, you can go to any plotting function and see this. If you have many sine function and cosine function, so let me say there is a sine function like this with certain amplitude, and there are other wave functions with different amplitudes or different wavelengths or the phases. Then if you sum of all those things would give you rise to a thing like this. So the same thing, if there is a discreteness, then we had used Fourier series. That's what you have studied in your BSc classes. But now we shall move on to Fourier integrals. Rather than whenever you had encountered with Fourier series, you had solved it using summation. So summation of coefficient was there and cos was there. So a omega cos omega t plus b omega sin omega t plus there was a naught which was there. So similar to that, there you started n from 1 to infinity. So here, rather than saying as a discrete thing, we will be doing with a continuous function. So therefore, we can integrate from 0 to infinity a of omega into cos omega t plus b of omega into sin omega t. So here, this a of omega is nothing but 1 by pi minus infinity to plus infinity f of nu cos omega nu d nu. So here nu is another integration variable. So just it is not a variable equivalent to t. So therefore, and b of omega is nothing but 1 by pi minus infinity to plus infinity f of nu sine omega nu d nu. So where f of nu is a function which you want to solve, for which you want to find the Fourier integral. So say for example, let us now take a pulse. So similar to what I had drawn earlier, this is a function with respect to t. So here just see this. There is a function with, if I draw t in x-axis and f of t in the y-axis. So here mod t, if it is greater than 1, then it is 0, and between minus 1 and plus 1. So mod t less than or equal to 1 means between minus 1 and plus 1. So if my 0 is here, so if I draw f of t and my t is here, 0 is this point and this is f of t, then mod t means plus or minus t. If it is less than minus 1, less than 1, that means the function which lies between minus 1 and plus 1 is 1 and it is 0 everywhere else. That's what this step function means. So this is a single pulse. It just, if you just see a pulse, before minus 1 there was nothing and after plus 1 there is nothing. Between minus 1 and plus 1 we see a pulse which is just going up to 1. So that is represented mathematically with this function. F of t is equal to 1 if mod t is less than or equal to 1. F of t is equal to 0 if mod t is greater than 1. Now, if we want to solve the Fourier integral for this, you have to first solve for a of omega. So a of omega is 1 by pi minus infinity to plus infinity f nu cos omega nu d nu, as I was stating earlier. So here the limit is from minus infinity to plus infinity. But if you see this step function, there is nothing after plus 1. So f of nu is 0. And there is nothing before minus 1. So f of nu before minus 1 is 0. So now the integral limit changes from minus 1 to plus 1. So therefore a of omega, Fourier integral coefficient a of omega, we can just write it as minus 1 to plus 1. F of nu in that region is 1 cos of omega nu d nu. So in other regions f of nu is 0. So integration of 0 is 0. So therefore we have left that term. Now if you integrate cos omega nu, what is the integration of cos omega nu? That is sine omega nu by omega. So we are integrating with d nu. So therefore we would be getting sine of omega nu by pi omega minus 1 to plus 1. So if you apply 1 and minus 1 as upper limit and lower limit in this case, you will be getting sine of, so you should know here you will be getting sine of my plus 1, that is sine of omega, which is upper limit, minus sine of minus omega by pi omega, right? What is sine of minus omega? It is minus sine omega. So here there is a minus. So therefore you can write that step as sine of omega minus into minus plus sine of omega divided by pi omega. So therefore we are getting 2 sine omega by pi omega as our coefficient, integral coefficient a omega. Then if you see here b of omega is 1 by pi f nu minus infinity to infinity f nu sine of omega nu into d nu. So which we can write it as 1 by pi minus 1 to 1 sine of omega nu d nu. So now if you apply this, you will be getting minus cos of omega nu divided by pi omega between minus 1 and plus 1. So if you integrate, if you apply the limits here, so cos of minus theta is what? Cos theta. So therefore, if you apply that limit here, because cos of theta is cos of minus theta is equal to cos theta. So therefore, here you will be getting minus 1 by pi omega we can take outside, and what we get is cos of omega minus cos of omega, because cos of minus omega is cos omega itself. So therefore cos omega minus cos omega is 0. Therefore you will get b of omega to be equal to 0. Therefore we can write Fourier integral f of t as 2 by pi. Here you can see this is a omega. So our Fourier integral was a omega cos omega t plus b omega sin omega t of d omega. Because b omega now it is 0, we are left with a omega cos omega t into d omega. So just apply that. Then f of t would be equal to 2 by pi 0 to infinity sin omega cos omega t by omega into d omega. Here you should be I mean, one of the things is by solving the integral, you can arrive at b of omega is equal to 0. The other way is just by seeing the function and seeing and actually verifying whether it is an odd function or an even function. You can actually get into this, and you can, by seeing whether it's an odd function or even function, you can decide whether a coefficient would exist or not. Do anybody tell me what is an odd function or what is an even function? So odd function is one if you put f of t or f of minus t is equal to minus f of t, then that is an odd function. If f of minus t is equal to f of t itself, that is an even function, right? So depending on that, you can just say whether a of omega or b of omega would become yes. So some people are answering yes. So you can definitely say whether it a of omega becomes 0 or b of omega becomes 0. Now can you just tell me in this function, is it an odd function or an even function? Yeah, this is an even function. Fine. So again, here using this sort of a Fourier integral, we can actually solve complicated equations like this. So by applying the limits, I'll be discussing one or two problems if time permits regarding this sort of Fourier integrals. So, so as I was telling, this is a Fourier integral approximation. So the moment we say we are saying the summation, there are so many waves. We can give omega any value between 0 and infinity. We are integrating that. When we integrate that, we would be getting a term like this. So this is what the Fourier integral as a whole was. Now there is what is called Fourier cosine and Fourier sine integral. So here, as I was telling in the earlier case itself, whenever we get even function, then we can approximate it by Fourier cosine integral, because b of omega would become 0 in that case. Rather, if we take the odd function, then we would be getting only the other term. When if you write this as b, then a of omega would be equal to 0. So therefore, for odd functions, you can actually simplify it, because b of omega would be 0. So therefore, you can just say that as Fourier sine integral. Do you know, in a function, I mean, if I give a function, a graphical representation of the function, do you know how to find whether it's in even or odd? Anybody in Google Meet can unmute and tell? Yeah, how? Now, yeah, if I give you a function, can you tell me whether it's an even function or an odd function if I give you a graph? Say, for example, if I give you a graph like this. Is this an even function or an odd function? This is, say, y and this is x. Yeah. Okay. Is this an even function or an odd function? Yes. So the thing is, if it is symmetric about y-axis, you can classify that as even function. If it is symmetric about the origin, then that is an odd function. Say if I give you a function which is neither symmetric about the origin nor symmetric about the y-axis, then is it possible to decide whether it's an even function or odd function? Yes or no? So if we have, yeah, it is, I mean, if it is neither symmetric about y-axis nor if it is not symmetric about the origin, then it is neither odd nor even. In those cases, this a of omega and b of omega, both of them will exist. That means to say, you cannot categorize that as cosine integral or sine integral. If you want to go for a cosine integral or sine integral, then any one of the coefficients has to be equal to 0. So otherwise, if it is not even or neither even or odd, then you have to solve the total Fourier equation, Fourier integral, which is f of t, right? Which is this one. So therefore, in some of the functions, rather than multiplying with cosine or defining it in terms of cosine or sine, it would be easier to express it in terms of the complex Fourier integral. So therefore, if you can express it in terms of complex numbers, some of the terms can be easily simplified and you can get it. So now let us see, and till now you have to remember that if it is neither odd nor even, then you have to go for total, or if it is even, then you can directly solve it using Fourier cosine integral. For the odd functions, you can approximate by using Fourier sine integral. Now we shall see how we can represent this Fourier integral in complex form. You know, this total integral f of t is integral from minus infinity to plus infinity, and I mean 0 to infinity a of omega cos omega t plus b of omega sin omega t d omega, and a of omega is 1 by pi minus infinity to infinity, and f of nu and all those things you know. We have already seen cos of omega t can be expressed in terms of Fourier cosine, I mean, cos of omega t in terms of e of omega e power I omega t as half of e of I omega t plus e power minus I omega t, and sine as 1 by 2i e power I omega t minus e power minus I omega t. This you can get because the very way we have defined e power I omega t, if you remember the complex numbers, it was like e power I omega t was defined as cos of omega t plus I sine omega t, and e power minus I omega t let me write here, e power minus I omega t was defined as cos of omega t minus I sine of omega t, right? So if you solve these things, you will get cos of omega t as half of the half of e power I omega t plus e power minus I omega t, and sine of omega t as 1 by 2i e power I omega t minus e power minus I omega t. So just substitute that. So therefore, we can write f of t as integral 0 to infinity c of omega e power I omega t plus d of omega e power minus I omega t d omega. Now we have to express c of omega. What we get? Now express C of omega as half of A omega minus IB omega. So A omega, we have already seen the integral, which is 1 by 2 pi into minus, because this one, minus infinity to infinity f of nu cos omega nu d nu minus I of minus infinity to infinity f of nu sin omega nu d nu. So therefore, if you take the cos omega nu and minus I sin omega nu on one side, you will be getting as minus infinity to infinity f nu e power I omega nu from the definition of e power I omega nu or I omega t. So therefore, C of omega we have got it as 1 by 2 pi minus infinity to infinity f of nu e power minus I omega nu d nu. So d of omega, if we represent it as half of A omega plus IB omega. So A omega and B omega contains the coefficient 1 by pi. So therefore 1 by pi can be taken outside. So half is already there. So it is 1 by 2 pi minus infinity to infinity f of nu cos omega nu d nu plus I minus infinity to infinity f of nu sin omega nu d nu. So similarly, using the definition, you can simplify this as minus infinity to infinity f of nu e power I omega nu d nu. So which was nothing but, just observe here, this is a minus sign and this is plus e power I omega nu. So therefore, this term that we are seeing here is nothing but C of minus omega. So therefore, we can write our Fourier integral rather than writing this. We can just write it as f of t is equal to minus infinity to infinity C of omega e power plus omega t d omega. Here you should be careful. Here observe the integral was from 0 to infinity. So C of minus omega, d of omega is nothing but C of minus omega and e power minus omega t is there. So rather than saying from 0 to infinity, you can say 0 to minus infinity of C of minus omega e power minus omega t. So therefore, these two terms got reduced to this C of omega e power I omega t d omega. And observe the coefficient C omega. Here also the integral is from minus infinity to infinity and the coefficient is 1 by 2 pi. Whereas for A of omega and B of omega, we took 1 by pi, and the integral from 0 to infinity. So therefore, the complex Fourier integral or Fourier integral in complex form can be expressed as f of t is equal to minus infinity to plus infinity C of omega e power I omega t d omega, where C of omega is 1 by 2 pi minus infinity to infinity f of nu e power I omega nu d nu. So now we have seen how to transform from cosine and sine forms. Now we shall see the inverse sine and cosine transforms. So the moment you say transform, you are going from one set of variables to the other set of variables, or to be specific, one domain to other domain. So have you heard of Fourier transforms in any practical situations? Anybody who have come across? Yes. So what are the two domains in which you are using that in digital signal processing? Yes. So you are going between time domain and frequency domain. Say for example, even in spectroscopy, I mean wherever the digital signals are involved, we go from one domain to the other domain. So it is very important because in some of the cases, if we get the range or in the frequency domain, we can analyze the things much more easily than in the time domain. What we measure will be there in the time domain. Say, for example, I am speaking. Over time, if you take the signals that I am producing, that would be in time domain. Then, if you give a function f of t for what I have spoken, the function that I have produced, the waves that I have produced, then multiply with e power minus I omega t and integrate from minus infinity to infinity into dt, then you will be getting the function in frequency domain. That means to say, first you have to understand when we say an integration, it is taking the sum over all the range. That means to say taking the area under the curve. So if you take the area under the curve, you would get a function which would be defined in frequency domain. Say if you want to take a realistic example, say if we have a free induction decay curve. That means to say a decay curve which is going like this. So we don't know which are the frequencies which have got main component in this and which are the frequencies which have got a lesser component in this. Rather than saying that, I cannot say by just seeing this sort of a wave, I cannot say that we have got, a frequency, a function depends majorly on 250 kilohertz or 250 hertz. I cannot directly conclude that because this is in time domain and this is a function f of t. Rather, if I multiply this with the function f of t with e power minus I omega t and integrate in the sense from minus infinity to infinity, whatever the function which I have received from any of the instruments, then I would get a frequency domain. So in frequency domain, if I see, then so wherever the functions are mainly contributing to this one would show a different value. Say, for example, the frequency at this has got more intensity than the second one. That can be understood from this. Let me say this is omega 1 and this is omega 2. So therefore, I can say that in the wave that has been produced by the machine that I am using, so there is omega 1 at a particular place. So omega 1 is contributing more than omega 2. So here I'm actually plotting omega versus f of omega. So I can clearly say which frequency is contributing more. So through this, you can even go for molecular analysis. This is what they do in NMR, FTNMR, FTIR. In all those things with respect to time, they actually measure the curves. How the function varies. That is called free induction decay curve. And then they integrate it. And all these things they are not going to do manually. The compute for software will be there that will be actually analyzing the signal that has been received. Okay, so that signal the computer would be receiving and then it would be integrating with respect to t over minus infinity to plus infinity. The moment we say minus infinity to plus infinity, we need not have to think that always it should be a very large value. Say, for example, if I am working in the range, say 200 to 300 frequency 200 to 300 hertz. For me, 10 kilohertz and minus 10 kilohertz or minus infinity and plus infinity because my range of data is very less. So between that, it would integrate, and after integration, it would actually give the final spectrum. The spectrum that we see has already been converted into the domain which we can read and analyze. So therefore, in all the cases wherever you see FT, Fourier transform of say NMR or IR, in almost all the spectroscopic instruments, it is Fourier transform that is being done to analyze the actual spectrum that you get from the instrument. So therefore, this Fourier transform becomes very much important. So to manually do that transformation, if we have f of t in the time domain, then f of t into e power minus I omega t dt integrate that between minus infinity to plus infinity and multiply with the factor 1 by root 2 pi to get f of omega. Here, f of t is 1 by root 2 pi minus infinity to plus infinity f of omega e power plus omega t into d omega. So, other examples are Dirac delta function. So, if you take Dirac delta function, so the moment you say delta function, it would spike at a point, and if you go below that or above that, it would be just like a single line. Below that and above that, it will not have any value. So that's what this delta function is. So delta of t minus a is equal to 0 if t is less than a or t is greater than a, and it is equal to 1 if t is equal to a. So now if we take Fourier transform of this, because here we are converting from time domain to frequency domain. So it would be 1 by root 2 pi minus infinity to infinity delta of t minus a e power I omega t dt. So if you integrate this, so here minus infinity to infinity is there, but except at t is equal to a, in all other places this would be 0. And that therefore you will be getting 1 by root 2 pi e power minus omega a. Or in particular, if a is equal to 0, that means if you are taking with an axis, then f of delta t or the Fourier transform of the delta function would be 1 by root 2 pi. So similarly, if you consider a Fourier transform of function f of t, which exists only between minus pi and plus pi, this is simply like this. So if I consider this as 0 and t is in the x-axis and f of t is in the y-axis, then only between minus pi and plus pi it is equal to 1, and above and below it, it is 0. It is a step function. So now if we consider this, if you want to take the Fourier transform for this, so this would be f of omega is equal to 1 by root 2 pi minus infinity to plus infinity f of t e power minus omega t. So here you should be careful that the function exists only between minus pi and plus pi. So rather than saying minus infinity and plus infinity, this would be going towards minus infinity, this would be going towards plus infinity. But in all other cases except between minus pi and pi, f of t is equal to 0. So therefore, f of omega we can write it as 1 by root 2 pi into integral of minus pi to pi e power minus omega t dt. So if you integrate e power minus omega t with respect to dt, then you would be getting e power minus omega t by minus I omega. So apply the limits minus pi to pi. So if you apply that, it would be I by omega into root 2 pi e power minus I omega pi minus e power plus I omega pi. So therefore, so here just apply e power minus I omega pi as cos omega pi minus sin omega pi minus of cos omega pi minus plus sin plus I sin omega pi. So here there is a minus here. If you apply here, I by omega into root 2 pi is here, and this one would be cos omega pi minus I sin omega pi minus cos omega pi plus I sin omega pi. Right? If we apply that, because cos has got cos of minus omega pi is nothing but, I mean, cos omega pi. Therefore, here minus minus goes. So cos omega pi minus cos omega pi, we can cancel it. And here minus into plus is minus. So therefore, we are left with minus 2i sine omega pi. And here minus 2 omega pi, 2i into I is nothing but I square is nothing but minus 1, because I is root of minus 1. So therefore, we are I square is minus 1. So minus into minus plus, we are left with 2 by omega into root 2 pi sine of omega pi. So depending on the frequency, you can actually get the variation in terms of sine. So similar to this cosine and sine integrals, we have got cosine and sine transforms. Rather than the transformation also, if the function that we get is even or odd, depending on that, we would be getting only a factor which contains sine or a factor which contains cosine. So if we have got an even function, then you can write f of t as in 0 to infinity a omega cos omega t d omega, with a of omega as 2 by pi 0 to infinity f of nu cos omega nu d nu. Now let us define another function fc of omega as fc of omega root of pi by 2 a omega. So here wherever nu is there, let us replace that with t. Then we will be getting fc of omega is equal to, then we will be getting fc of omega is equal to root 2 by pi 0 to infinity f of t cos omega t dt, where f of t is root 2 by pi 0 to infinity f of c of omega cos omega t d omega. So observe here, here there is dt, here there is d omega. So this is called, the equation 7 is called the Fourier cosine transform of the function f of t. Or if you take the equation 8, where we are going from the frequency domain to the time domain, it is called inverse Fourier cosine transform. So the same thing what we have expressed in terms of complex integral, I mean, where we have used e power I omega t and e power minus I omega t, here we are taking the records of cos and sine. So therefore, these are Fourier cosine transform, and similarly, we can define Fourier sine transform. So similar to what the Fourier cosine transform, we can define the Fourier sine transform. So here we are taking the odd function. So because we are taking the odd function, a of omega would be 0. So we have to deal only with b of omega. So f of t is equal to integral 0 to infinity b of omega sine of omega t d omega, where b of omega is equal to 2 by pi 0 to infinity f of nu sine of omega nu d nu. Similar to what we did in the case of the cosine transform, let us define a function fs of omega which is equal to root of pi by 2 d omega, b of omega, and replace nu by t. Then we get the Fourier sine transform of function f of t as root of 2 by pi 0 to infinity f of t sine of omega t dt, and ft we can represent as root of 2 pi 0 to infinity fs of omega sine omega t d omega. So here the first one is sine transform itself, and the second is inverse Fourier transform. So To summarize, we call the going from omega t to, t, the time domain, to the frequency domain as the sine, cosine, or the Fourier transform, and the other one as the inverse Fourier sine, cosine, or the Fourier transform. Here you should remember, if you want to go for either Fourier sine transform or Fourier cosine transform, you should have an even or an odd function respectively. So be aware of that and then go for the transformation. Even if you get a problem and if you cannot identify a function as even or odd, you can directly go for a generalized complex form or the Fourier integral. If they have asked, you can go for the generalized formula where there is a of omega and b of omega. Both the terms are there. Then you can simplify it. You will definitely get the things. So if it is an even function, then only a of omega remains. The term which is, the coefficient which is corresponding with that of cos term would be remaining, and the one with the sine term, that is b of omega, would be vanishing. Similarly, if it is an odd function, then b of omega remains and a of omega will be vanished, or a of omega will be 0. So there are certain rules for this transformation. So before we go into that, we shall look into certain problems. So coming to the Fourier sine and Fourier cosine integrals. So here there is a problem where from 0 to pi, a function is a step function. So here I am considering x and f of x, and f of x is 1 from 0 to pi. Let me consider this as pi, and above it, it is 0. So using this function as a Fourier integral, and we have to evaluate a complex integral 0 to infinity 1 minus cos pi of lambda by lambda sine x lambda d lambda, right? So as I was telling when doing with the Fourier integral, so as an application we can use this to actually solve complex complex integrals. So this is a very complex integral, 0 to infinity 1 minus cos pi lambda by lambda. So therefore we shall solve this. So here the Fourier sine integral, I mean rather than just seeing that as a term in which we get only in terms of functions, if we get a similar kind of functions, we can actually use the boundary conditions or the functions which would actually express this integral. We can solve complex integrals like this. So here Fourier sine integral f of x is equal to 2 by pi 0 to infinity sine of lambda x d lambda 0 to infinity f of t sine of lambda t dt. So just simplify this. So 2 by pi 0 to infinity sine of lambda x d lambda and 0 to infinity sine lambda t d lambda. So now integrate one of them. So sine lambda t into dt would be minus cos lambda t by lambda, and apply the limits. So as the problem says, beyond pi, this f of x does not exist. So therefore, we have to take the integral limits as 0 and pi. So apply that. So let the other term be here. So here if you observe, we have taken the coefficient and the integral in one step itself. So therefore it is 2 by pi 0 to infinity 1 minus cos lambda pi by lambda. So you have to remember cos of 0 is 0 cos of 0 is 1, whereas sine of 0 is 0. So therefore, we are getting 1 minus cos of lambda pi by lambda into sine of lambda x d lambda. So in the question, we are supposed to solve an integral 0 to infinity 1 minus cos of pi lambda by lambda into sine of x lambda into d lambda. So apply that. So here, if you see the function pi by 2 into f of x, that's what we are remained with. So this is nothing but f of x, right? Or rather, let me write the f of x using the sine integral. We have found that f of x to be 2 by pi 0 to infinity 1 minus cos lambda pi by lambda sine lambda x d lambda. Take the other way around. We want this integral only. So 2 by pi we are taking to the other side. So therefore it is pi by 2 f of x. So therefore this integral f of x, what we have defined was from it is 1 between 0 and pi, and elsewhere it is only 0. So therefore this integral would be pi by 2 for the range 0 to x, and it is 0 elsewhere. So if we want to find out what would happen at pi, we shall take pi by 2. So f of x, f of pi approaching from minus side plus f of pi, f approaching from the plus pi. So from plus 0 and minus 0, if you take at pi, because if you consider here at pi, so you have heard of limits, right? So whenever we want to take that, we would be taking it from negative and the positive side approaching to the pi itself. So f of pi minus 0 plus f of pi plus 0 by 2 would be pi by 2 plus, so pi plus 0 is 0 and pi minus 0 is 1, because before, if it approaches from the left hand side, it has got the 1, because here it is 1, and if it is approaching from right hand side towards 0, then it is 0. That's what the function is. So at pi, if we divide it into the two components, which one of which is approaching from the left and one from which is approaching from the right, we would get 1 plus 0 by 2, which is 1 by 2 into pi by 2 would give us the value pi by 4. So therefore, we have solved a complex integral, which is 0 to infinity 1 minus cos of lambda pi by lambda sine of lambda x d lambda at pi as pi by 4. So rather, if you had taken the regular integral, so you should have multiplied with sine of lambda x, and in the second term here, you would have got two terms containing cos and sine, and then you should have integrated by parts, and you should have applied the limits, and then you should be finally finding out what would be the function. But using Fourier sine series, we are able to find out how this integral would be after you solve this integral. So in Fourier transform, now let us see certain properties of Fourier transform. So we can go step by step. So these are certain Fourier transforms. As I was telling that whenever you go for Fourier transforms, so depending on the function in the time domain, you can observe a different kind of function in the frequency domain. Here the signals are in the time domain and the frequency domain or the Fourier transformed one. The first function is just a cosine function. If you integrate a cosine function, you would just get a peak at certain omega because it contains only one omega. This you can decide clearly because here if you take the integral of it, there will be plus and minus, and depending on what is the omega which you have got, you will be getting a peak in that omega, the dominating frequency. So sine function, you will be getting uniform band of frequencies. For Gaussian function, you will be getting Gaussian function itself. So if you solve something like e power minus x square by 2 into e power plus or minus I omega t into d omega, you will be getting the Gaussian function itself. So same in the same way, if you have double exponential function, you'll be getting a Lorentzian function. Here a Lorentzian function is a peak, a slightly broadened one, whereas Gaussian has got much more broadening, whereas the Lorentzian function has got a slight broadening. So double exponential function is the one so which has got exponentially decreasing function on both the sides. When you go away from the center, on both the sides you will get an exponentially decreasing function. So if you take that sort of a function in the time domain, then Lorentzian function would be the resulting function in the frequency domain. So let us solve one or two problems in Fourier transform. So here a similar kind of function in which mod of x is less than 1. For that, the function value has got 1 and elsewhere it is 0. That means to say, if we have got a function, so similar to what we have defined over there, something like this. If this is f of x and this is x, from minus 1 to 1, there is a step function, elsewhere it is 0. Rather than, we have already seen this sort of function, rather than just solving this as a Fourier transform, we have to evaluate a function sine x by x dx integrated between 0 to infinity. So here Fourier transform of f of x is integral minus infinity to infinity f of e power isx here rather than omega, they are calling it as s. So sx dx. So here between minus 1 to 1, the function is 1, otherwise it is 0. So therefore, the limit we are taking it from minus 1 to 1, e power isx dx. So e power isx by is would be the integral of it. Take the limit from minus 1 to 1. If you apply that, you will be getting e power is minus e power minus is by is. So therefore, the Fourier transform of this function would be 2 of sine s by s. If you remember, sine x or sine omega t, we have defined it as e power I omega t minus e power minus I omega t by I omega t 2 times by 2 I omega t. So there is no 2 in the denominator here. So therefore, it is multiple of 2. So this is one way of solving it using the generalized complex Fourier transform. But here itself, if you observe this function, you can directly solve it because it is symmetric about y-axis. Any of the two methods you can use to solve this. So we have got 2 sin s by s, and it cannot make s equal to 0. If you want to make s to be equal to 0, you should be careful. You have to apply the limits, and we have if you remember from your plus 2 itself, Always they have been telling sin x by x, as the limit x tends to 0, it would be 1. So that is a standard limit which you would have solved in your plus 2. So therefore sin s by s, as s tends to 0, would be 1. Limit as s tends to 0, sine of, see, if you call this as x, sin x by x is equal to 1. So therefore f of s at s is equal to 0 is 2. Now we have to find out the integral. There are two parts to this function. One part is solving this Fourier transform. The other part is to solve the integral 0 to infinity sin x by x dx. Okay, so to do this, let us consider the inverse Fourier transform. Okay, we have already got what is f of s. So we shall solve it for f of x. So here s and x are the two domains between which we are considering the Fourier transform. So therefore f of x is equal to 1 by 2 pi minus infinity to infinity f of s e power minus sx ds. Please do see here, when you consider e power I sx, you are integrating with respect to dx, and now the inverse of it you are making. So one thing is the sign of the power. Initially it was e power plus I sine I sx, next it is e power minus I sx. And here you are integrating with the variable x, the domain x, because you are going from domain x to domain s, and now because you want to go back to the domain x, you are integrating with respect to ds, that is s. So you should take care of the sign of the e power and the variable with which you are going to integrate, whatever might be the problem. So you should take, if you take care of those two, the other thing which is remaining is only solving the integral and applying the limits. So f of s, we have already found it as 2 sine s by s. So apply that. So f of x would be 1 by 2 pi minus infinity to infinity 2 sine s by s e power minus I sine x into ds. So if you integrate this, we have already seen the function as f of x is 1 for x less than 1, and f of x is 0 for all other values. So therefore this would be minus 1 for x less than 1, mod x less than 1, and 0 for mod x greater than 1. So that's where we have started with f of x. So therefore by putting x is equal to 0, we get sine s by s ds, because e power of 0 is 1, we would be getting it as pi. Therefore 0 to infinity. So here if you see here, from minus infinity to infinity, sine s ds. So therefore if you are taking the integral on one side, it would be half of the total integral. So therefore you would be getting 0 to infinity sin s by s into ds as pi by 2. This we can do because it is an even function. Fine. So rather than this, if you had solved using Fourier sine transform also, you would have got the same equation. So to summarize this, what we have done is, we have first taken the Fourier transform of a function, and then we have found out what are the things what are the limits for that, and then we have taken the inverse Fourier transform to get the function in terms of an integral form. And by doing that, we have solved the integral that we have got, which is integration of 0 to infinity sine x by x dx. So, what's the time now? 8:42. So, shall we solve one more problem? Yeah. So, if you want to find the Fourier transform, here the function, rather than saying just 0 and 1, we shall consider the function which is much more than this. So it is, say, we shall consider 1 minus x square in the mod of x less than or equal to 1 and 0 elsewhere, and hence solve a complicated integral. Right? So now, as usual, take Fourier transform of f of x to be minus infinity to infinity f of x e power I s x dx, which is f of s. So we have seen this mod of x, if it is greater than 1, then it is 0. So therefore, between minus infinity to minus 1, this integral happens to be 0. And from minus 1 to plus 1, this happens to be f of x is 1 minus x square. And again, from 1 to infinity, it is 0. So we have to divide it to 3 domains. So beyond this, it is 0, and beyond this, it is 0, and in between, it acts like 1 minus x square as the function. Right? So consider that and apply the integrals. So if you integrate it, you would be getting, you have to integrate it by parts. So first function into integral of the second function minus differential of the first function into integral of the second function into the differential of the second function. Again, if you have got again some factors in that, you have to again apply the rule of integration by parts. So if you do that, you will get 1 minus x square into e power isx by is. Then if you apply that, you will be getting e power isx by is into differential of it, 2x. And again, there will be an integral which would be remaining. So again, apply the integration by parts rule. So that would be 2x into e power isx by is was initially only it was there. Again, if you integrate e power isx, you would be getting is whole square. And minus into minus plus of minus of e power isx by is whole cube into minus 2 between the limits minus 1 and plus 1. So now if you simplify this, you will be getting 2 into e power is plus e power minus is by s square minus 2 into e power is minus e power minus is by minus is cube. So if you simplify that, you will be getting 4 by s cube into s minus cos s minus sin s. So again, this is just the Fourier transform. If they ask you to just do the Fourier transform, you can stop at this stage. But we have to we have to take and determine the integration of another function. So therefore, take the inverse Fourier transform, which is f of x is equal to 1 by 2 pi minus infinity to plus infinity f of s e power minus sx dx. So then you take f of s, which you have determined in the previous step, which is 4 by s cube into s cos s minus sin s. So put those values. That should be your function, initial function that you have taken, which is 1 minus x square between minus 1 and plus 1, elsewhere it is 0. So therefore, apply the limits. Now let us put x is equal to half, and because we have to determine this equation. So put s is equal to half, x is equal to half, and apply the limits. You will be getting e power minus is by 2 ds, which happens to be 3 by 4, which is 1 minus 1 by 4 is 3 by 4. So then again simplify this. E power minus is by 2 as cos s by 2 minus I sin s by 2, which would be equal to minus 3 pi by 8, because you have to take it to the other side. So here there is 2 and there is 4. 2 2s are 4. Take 2 to the other side and pi to the other side. You would be getting 3 pi minus 3 pi by 8. So cos s by 2 minus I sin s by 2 ds. So integrate it. You would be getting, instead of s, we can put x now, because it is a variable which we can change now. So x cos x minus sin x divided by x cube cos of x by 2 dx would be minus 3 pi by 16 psi, because we are taking here minus infinity to plus infinity as in the previous problem. Because it is an even function, we can take half of it, right? So therefore 3 pi by 8 into half is 3 pi by 16. So this is what I was speaking about, the Gaussian function. Gaussian function is some constant e power some constant of minus x square into some constant, or minus x square by 2, or x square by a, or minus a square into x. So if you take the Fourier transform of this, you would get a form which would actually reciprocate e power, or that means you would get a function which has got e power minus x square itself. So that is what is called self-reciprocal with respect to Fourier transform. I mean, even in the other domain, you would get a function of a. So if you go for solving this, the Fourier transform of this sort of a function, you can take e power isx and solve it. You'll get back to e power minus s square by 2. So apart from this, if you go for the properties of Fourier transform, you have to study properties with respect to the derivatives. Somebody has unmuted yourself. Please mute. Yeah. So if I take the Fourier transform of a derivative of a function, so just apply this. So let us take Fourier sine or cosine and simply solve this, so that you will be knowing what sort of a function you will be getting if you take the Fourier cosine transform and Fourier sine transform for the derivative of a function. So now we have seen, instead of f of x, we have got df by dt of f of, right? So here we shall take Fourier cosine transform. That would be root of 2 by pi 0 to infinity d by dt of f of t cos omega t dt. Now integrate by parts. So when you integrate it by parts, you should choose functions clearly. Which one you want to choose it as the first function and which one as the second function. So here, because we are taking the first function into integral of the second function, so here choose d by dt of f of t as your second function so that you can, when you integrate it, you will be getting the f of t. So if we do that, cos of omega t into integral of d by dt f of t dt, you will be getting f of t itself. So this is just like this, cos of omega t into integral of d of f of t by dt into dt. It is integrating a differential with respect to the same variable. So therefore, you will be getting it as cos of omega t into f. So f of t cos of omega t between 0 to infinity plus omega of 0 to infinity f of t sine of omega t. So you have to take the differential of this into dt. So as t tends to infinity, we have got the definition like when t is infinity, there is no function which exists at infinity. So therefore, the upper limit, which is infinity, as t tends to infinity, f of infinity becomes 0. So therefore, we are only left with lower limit. We can write this as minus root of 2 by pi f of 0 plus omega fs of f of t. So if you observe the second term, I mean, when you differentiate, the coefficient with respect to cos would be there as a multiple. So differential of cos of omega t is omega sin omega t. I mean minus omega sin omega t. So if you observe this, this is a Fourier sine transform. So therefore, we can write the Fourier cosine transform of a differential of a function is nothing but the minus root 2 by pi f of 0 plus omega of Fourier sine transform of the same function. Whereas, if you take the Fourier sine transform, so do the similar exercise. Here you will have 2 by pi 0 to infinity d by dt f of t sin omega t dt. Here we would be integrating it by parts. So root of 2 by pi f of t sin of omega t going from 0 to infinity minus omega 0 to infinity f of t cos of omega t dt. Here one thing is, as t tends to infinity, f of t would be 0. That means f of infinity is 0. So upper limit vanishes. And when you apply the lower limit, sine of 0 is 0. So both the upper limit, when you apply the upper limit and the lower limit, the first term vanishes. It becomes 0. So therefore, you are only left with minus omega Fourier transform of the function. So therefore, if you apply the Fourier cosine transform for a function, derivative of a function, you will get minus root 2 by pi f of 0 plus omega Fourier sine transform of the function. Whereas if you apply the Fourier sine transform for a derivative of a function, you will get minus omega Fourier cosine transform of the same function. So this is what the thing is. So similarly, if you apply the same thing for the derivative, second derivative, again, though, so if f of t itself tends to 0, f dash of t when t tends to infinity, then also it is 0. Now apply this to the second derivative. So the second derivative, if we represent first derivative as f dash, if you take d by dt of f dash, then it would be omega Fourier sine transform of f dash minus root 2 pi f dash of 0. If you apply the Fourier sine transform, here see Fourier sine transform to a derivative. So f dash is a derivative. If you apply that, you would get minus omega Fourier cosine transform of f of c. I mean, cosine transform of the function. So therefore, if you apply for the second derivative, you will be getting minus omega square Fourier cosine transform of the function itself minus root of 2 by pi f dash of 0. That means to say, if you want to Fourier transform the second derivative, if you know the first derivative at 0 and the Fourier cosine transform of the function itself, you can say what is the Fourier cosine transform of the second derivative. Similarly, if you apply the Fourier sine transform for this second derivative, you would be getting minus omega square Fourier sine transform of the function plus omega into root 2 by pi f of 0. So it is just like this. Let us consider an example of how much time do I have? Let us consider an example of d square by dt square e power minus a omega t. If you do that, if you take the differential, whatever coefficient which is there in the power would be a multiple of it. So if I take d by dt of e power minus at, it would be minus a into e power minus at. If I differentiate again, then minus into minus, it would be plus a square e power minus at. So if we want to take the Fourier transform of this function, Fourier cosine transform, then because a square is a constant, you can take it out. So a square into Fourier cosine transform of e power minus at would be equal to minus omega square Fourier cosine transform of e power minus at minus root of 2 by pi into when it is f dash of, so here f is e power minus at. So the first derivative f dash would be minus a e power minus at, and f double dash is nothing but minus a into minus a e power minus at, which happens to be a square e power minus at. So now from the formula, if you see, this is f dash of 0. So what is f dash of 0? I mean, wherever t is there, we have to put 0. So therefore, f dash of 0, we can write it as minus a e power minus a into 0. So e power 0 is 1. Therefore, we are left with minus a. So here, if you consider minus of root of 2 by pi into minus a e power 0 is nothing but 1. So therefore, plus root of 2 by pi. If you see here, we have got Fourier cosine transform on both the sides. Take it to one side and take the common factor, which happens to be a square plus omega square. So therefore, the Fourier cosine transform of e power at, you can simply write it as root of 2 by pi into a by a square plus omega square. So this is a simple way of solving the functions which repeats themselves after deriving it for 2 times. This sort of functions you can observe like in trigonometric functions like sine and cos. If you differentiate twice with a coefficient, the same function you will be getting back. So similarly, e power. For such sort of a function, if you know the Fourier transform may be cosine or sine transform of e power or the sine or cos depending on the function. If you have that, you can use this formula or the property of derivative of a Fourier transform to get the Fourier cosine transform itself. Fine. What's the time now? Oh, 9 o'clock. Fine. You can refer any of the mathematical physics books. Sometimes you will get mathematical methods for physicists books, or mathematical physics books, or higher engineering mathematics books for solving more problems on this topic, Fourier transforms. Fine. So are there any doubts? So if you have no doubts, we shall end today's session. In the next session, we shall complete this Fourier transform and we shall go to the other topics, which is a vector space, which is a complex space. You would have studied in mathematics classes the rings on all those structures, the groups, rings, and then fields, and then the spaces. We shall define the vector spaces, the space with respect to certain fields, and we shall also see how we can get a we can actually identify a linearly dependent or independent functions, right? And also that would be the basis for understanding or solving the problems in quantum mechanics, because the Hilbert space in which we consider all the quantum mechanical relations is a complex vector space. So therefore, we have to study vector spaces. In the next class, we shall study that. Fine. So if you have no doubts, we shall end this session. Yeah. Thank you all for listening. Fine.